Computer science encompasses the study of computation, information, and automation across various disciplines, from theoretical aspects like algorithms, theory of computation, and information theory to more practical applications such as hardware and software design and implementation. Experts in this field are known as computer scientists. The central focus of computer science is to determine what tasks can be automated. The Turing Award is considered the highest honor in the field. The roots of computer science can be traced back to historical figures such as Gottfried Wilhelm Leibniz, often called the founder of computer science, and Charles Babbage, referred to as the father of computing. Ada Lovelace, known for publishing the first algorithm for computer processing, also made significant contributions. Early innovations in mechanical calculators by Wilhelm Schickard and Gottfried Leibniz laid the groundwork for modern computing. Charles Babbage's designs for the difference engine and analytical engine pioneered the concept of programmable mechanical calculators utilizing punched card systems, with Ada Lovelace creating algorithms for implementation. Subsequent advancements by Herman Hollerith, Percy Ludgate, and Leonardo Torres Quevedo further contributed to the evolution of computing technologies. In the 20th century, pioneers like Howard Aiken and developments like the Atanasoff Berry computer and ENIAC marked a shift towards electronic computing machines. IBM's establishment of the Watson Scientific Computing Laboratory at Columbia University in 1945 and the subsequent collaboration between academia and industry played a significant role in the growth of computer science as an academic discipline. The first computer science degree program was initiated at the University of Cambridge in 1953, with the United States seeing the formation of the first computer science department at Purdue University in 1962. As practical computers became more widespread, various specialized areas within computer science emerged, leading to the establishment of distinct fields of study. The term computer science was first proposed in 1956 but gained popularity after appearing in a 1959 article by Louis Fine. Lewis argued for the establishment of a graduate school in computer sciences akin to Harvard Business School. This initiative, supported by figures like numerical analyst George Forsyth, led to the creation of computer science departments in universities, starting with Purdue in 1962. Interestingly, despite its name, a significant portion of computer science does not directly involve the study of computers, prompting the consideration of alternative names like computing science and datalogy, which focus on different aspects of the discipline. The development of computer science saw the emergence of various terms to refer to practitioners in the field, reflecting different perspectives on the nature of the discipline. The relationship between computer science and other related disciplines like mathematics, engineering, and software engineering has been a subject of debate, with varying viewpoints on the core focus and principles of these fields. Additionally, the classification of computer science as a science, mathematics, or engineering discipline remains a topic of discussion among scholars, each perspective offering unique insights into the nature of computational systems and their study. Various paradigms have been proposed to define the foundations of computer science, including science, technology, mathematics, theory, abstraction, and design, each highlighting different aspects of the methods and approaches used in the field. Computer science encompasses a wide range of activities, from design and specification to programming, verification, implementation, and testing of artificial computing systems, demonstrating its interdisciplinary nature and its connections to diverse fields such as cognitive science, linguistics, mathematics, and philosophy. Computer science encompasses a wide array of subjects, from theoretical analysis of algorithms to the practical implementation of computing systems in both hardware and software. CSAB, previously known as the Computing Sciences Accreditation Board, consists of representatives from ACM and IEECS and recognizes 4 key areas critical to computer science: theory of computation, algorithms and data structures, programming methodology and languages, and computer elements and architecture. Additionally, CSAB acknowledges fields such as software engineering, artificial intelligence, computer networking and communication, database systems, parallel computation, human-computer interaction, computer graphics, operating systems, and numerical and symbolic computation as significant domains within computer science. Theoretical computer science is a discipline that is both mathematical and abstract, seeking to understand computation's nature to provide more effective methodologies. Theory of computation, a crucial aspect of computer science, focuses on determining what can be computed and the resources required for those computations. Computability theory examines solvability on different computational models, while computational complexity theory investigates the time and space costs of solving diverse computational problems. Information theory and coding theory, which delve into information quantification and the study of codes for data transmission methods, are closely related disciplines in computer science. They play key roles in various applications such as data compression, cryptography, error detection, and correction. Similarly, data structures and algorithms explore commonly used computational methods and their efficiency in the analysis of algorithms, algorithm design, data structures, and combinatorial optimization. Programming language theory and formal methods involve the design, analysis, and classification of programming languages. Computer graphics delves into the synthesis and manipulation of digital visual content, serving essential roles in fields like computer vision, image processing, and video games. This area includes 2D computer graphics, computer animation, rendering, virtual reality, and more. While data processing focuses on the central concept of informatics, studying information processing algorithms across different information carriers. In computational science, finance, and engineering, computer software is used to analyze and solve scientific problems through mathematical models and quantitative analysis techniques. This encompasses simulation of processes like computational fluid dynamics, electrical systems, biological interactions, and more, aiding in optimization and design processes. Software engineering entails designing, implementing, and modifying software to ensure high quality, affordability, maintainability, and efficiency. It applies engineering practices to software design, including aspects like software testing, systems engineering, technical debt, and software development processes. Artificial intelligence aims to replicate human-like problem-solving, decision-making, learning, and communication processes in machines. This interdisciplinary field incorporates areas such as computational learning theory, computer vision, neural networks, natural language processing, and robotics in its pursuits. Computer architecture and microarchitecture focus on the design and fundamental structure of computer systems, including processor components, personal computers, supercomputers, and embedded systems. This field addresses the internal operations and memory access of the central processing unit, crucial to understanding computational logic and hardware design. Bill Rappaport identified 3 key insights in the field of computer science. One crucial observation was made by Gottfried Wilhelm Leibniz, George Boole, Alan Turing, Claude Shannon, and Samuel Morse, stating that computers only need to work with 2 elements, typically 0 and 1, to represent any information related to a computable issue. Alan Turing's significant contribution highlighted that computers only require 5 fundamental actions to execute any task effectively, including moving left or right by one location, reading symbols, and printing either 0 or 1 at a given location. A further insight by Corrado Bohm and Giuseppe Jacopini emphasized that only 3 methods of combining these basic actions are necessary for a computer to perform tasks effectively, namely sequence, selection, and repetition. These rules can be further simplified using the go-to statement, which is considered more elementary than structured programming methodologies. The realm of programming paradigms encompasses various approaches like functional programming, which focuses on evaluating mathematical functions without mutable data; imperative programming, which involves changing a program's state through statements; object-oriented programming, centered around objects containing data and procedures to interact with each other; and service-oriented programming, where services form the unit of computing work to develop integrated applications and software programs.